Okay. So we're going to talk more about acids and bases. We're going to talk about applications of an understanding of their equilibrium. So applications of aqueous equilibrium. So we learned about the reactions between acids and bases in our last chapter. And now we're going to use that information a little bit more to understand the properties of acids and bases. So we learned that when you mix a strong acid and a strong base, and if you write a net ionic equation, what you're really reacting is hydronium cations with hydroxide anions to make water. And the pH will be 7. And the pH will be 7 because if you look at this, this is essentially the reverse reaction of the dissociation of water. So the K for this reaction would be 1 over Kw. And you can use that to figure out that the pH would be 7. You can also look at reactions of weak acids and strong bases. So if it's a strong base, we know that we can write it as OH minus. So if you go from the first reaction to the second, we completely dissociate the sodium hydroxide to make OH minus. But the weak acid, we don't dissociate because we know a weak acid means that that proton doesn't come off and form hydronium cations completely. And so when we write this reaction in the middle, it's a better representation that the weak acid is reacting with a strong base to make water and then leaving behind the conjugate base of that weak acid. In class, we will actually go through the process so we understand what the K would be for these reactions, these neutralization reactions. So what would the K be for this? It's not a Ka reaction. It's not a Kb reaction. So we'll go through the process of figuring out with Ks that we have what the K for this neutralization reaction will be. That way we'll be able to understand why the pH is going to be greater than 7. A weak acid and a strong base, that's the same exact reaction. They're just showing you that you can tell when they've completely reacted if you use an indicator like phenolphthalein, which will turn pink when the solution goes from acidic to basic. So this is a strong acid with a weak base, so kind of just the opposite. This was weak acid, strong base. Now this is strong acid, weak base. But it's the same idea. We will write the strong acid as H3O plus because we know if HCl is a strong acid, every one of those molecules that you put into water will form an H3O plus hydronium cation, which makes it acidic. And the weak base, we'll leave it written as it is because it doesn't dissociate. And this just shows you the net ionic equation for that process. And just like the last reaction in class, we'll go through the process of figuring out what would be the K, the equilibrium constant for that expression. And therefore, how would we know that the pH is going to be less than 7? Strong acid, weak base. This is just an example, another one where you're using an indicator that changes color when you go from, in this case, acidic to basic. And then weak acid, weak base. It's a little bit different, and you don't necessarily know what the pH is going to be. It depends on the relative strength of the weak acid and the weak base. So just like the others, we'll go through the process of getting a K for this reaction, and we'll see if we can figure out a pH. So we'll use these neutralization reactions in titration problems, which will help us identify acids and understand their properties, such as their Ka values. So that's why this is at the start of the chapter. We're going to use this information a little bit later. The other really important part of this chapter, because it basically defines what a buffer is something called the common ion effect. So we looked at the common ion effect back in our chapter on equilibrium. So it's the shift in the position of an equilibrium on addition of a substance that provides an ion in common with one of the ions already involved in the equilibrium. So if we look at this, for example, on the product side, we have this, it's called acetate anion. So the conjugate base of acetic acid, which is our acid over here, is called acetate. And if you put that, if you're looking at how much acetic acid dissociates, that would be this reaction. But if we added a whole bunch of sodium acetate, that would change our equilibrium expression. That will force it to not dissociate as much if we look at that problem in a little bit. So that is exactly what they're doing here. So we have acetic acid in water, but we've already put some of the acetate in. So they want us to calculate the pH of a solution that's prepared by dissolving 0.1 mole of acetic acid. So that's our reactant acid, and 0.1 mole of sodium acetate. So if you dissolve sodium acetate, you get the acetate anion in enough water to make a liter. So that means we start out with 0.1 molar of acetic acid and 0.1 molar of acetate. So it's the same exact problem. There's nothing new. It's just that with the common ion effect, each of the products don't start out at X or don't change by X. They do change by X. I'm sorry. They don't start out at 0. One starts out at 0 and one starts out at 0.10. So our equilibrium expression will be set up exactly the same way. It's a Ka reaction. But now in our numerator, rather than having X squared, we have X for the H3O plus concentration and 0.10 plus X for the acetate concentration. So when you solve that math, you get a hydronium cation concentration of 1.8 times 10 to the minus 5. And if you look at how they solved it by knowing that it's not going to go forward or backwards that much. So they said X has to be included in my calculation, but 0.1 plus X and 0.10 minus X, the X is probably going to be insignificant relative to the 0.1. So that means that the hydronium ion concentration is going to be equal to the Ka. Is that true? So now when you look at it, if you subtract 1.8 times 10 to the minus 5 from 0.10, you see that you wouldn't change 0.10 because this is in a digit we don't even know for the 0.10 concentration. So that was a good approximation in solving this, saved us a lot of time. And we can look at our answer always to confirm that it was a valid assumption. So just like any problem, common ion effect doesn't matter. Once you get the H3O plus concentration, you can take the negative log to get the pH. So the common ion effect is just showing you, what is it showing you? On the left-hand side, you have equal concentrations of acetic acid and acetate, which is the problem we just did. And on the right-hand side, we have pure acetic acid just dissociating. So with no common ion effect, you'd solve the problem with the same expression, but you'll get a different hydronium ion concentration. So Le Chatelet's principle really is just what the common ion effect is showing us, that if we have a reaction and we add either more reactant or product, the reaction is going to shift in order to alleviate that stress. So in this case, we have acetic acid dissociating in this reaction, but if we add some of the dissociated acetate, then it's going to force the equilibrium to go the other direction a little bit in order to keep the concentration ratio equal to the Ka. And so that tells us that the solution should have more acetic acid in it. Common ion effect, just showing you that as you add acetate, the product, you're forcing the reaction to go backwards. And so when you force the reaction to go backwards, that means you get less H3O plus, because in order for this reaction to go backwards, you have to use up the hydronium cation. So if we add some of this, Le Chatelet's principle says reaction will go back to reactants in order to alleviate the stress we've created. And in the process of doing that, we're going to decrease the concentration of H3O plus because that's needed in order to react this backwards. And so this graph is just showing you that you will have less H3O plus as you add more and more acetate. So the common ion effect is what I said is really the basis for any buffer. So all of you students who are going to major in molecular bio, especially, buffers are so important to living systems. And so a buffer is a solution that contains a weak acid and its conjugate base, and it resists drastic changes to pH. So your body is all filled with buffers. Your blood, every liquid or fluid in your system has to be buffered, so that if, for example, you eat something acidic or somehow you're exposed, your blood is exposed to something acidic or basic, you would want the pH to stay as constant as possible. So it has to be a buffered system in order to do that. So we'll look at why these systems work as buffers. So in each case, we have a weak acid, and it's only when it's the weak acid and its conjugate base that we have a buffer. So acetic acid and acetate will make a buffer. Hydrofluoric acid and fluoride ion will make a buffer. Ammonium cation and ammonia acid conjugate base. So in each of these cases, we can make a buffer because we have an acid and its conjugate base. And these are just showing you, the first one is that equilibrium. Yeah, so this is showing you how a buffer works. So if you have a buffer, so let's say we have equal concentrations of acetic acid and its conjugate base. If you add a little bit of OH minus, a strong base, it's going to react with some of the acid to make it into acetate. And so that will help take away the acidic or the basic properties of the OH minus by giving it something to react with. Whereas if you add some acid, then you have a weak base in here to react with that, and it will react to make some acetic acid, but it will alleviate the stress basically of adding this by reacting away some of the H3O plus. And when we look at the equilibrium constants for these, because this really is a neutralization reaction for a weak acid with a strong base, and this is a neutralization reaction for a weak base with a strong acid. So the reason they say they go to 100% completion, we'll see when we do this in class, where we look at these reactions and we actually determine what the K will be. And if the K is large, then we know it's valid to say that those reactions go about 100% to completion. So a buffer solution is not only a weak acid and its conjugate base, but they need to be in close to equal quantities, so that if you add some strong base, some of the conjugate acid will become conjugate base. And if you add some strong acid, it'll go the other direction. It will react with the base to make more of the conjugate acid. So as long as the concentration ratio stays close to its original value, the H3O plus hydronium cation and the pH won't change very much in either of these cases. These are just pictures of how colors change if the pH changes and if you have a buffered solution. So yeah, the first, it doesn't tell us what the buffered solution is, but what it's trying to show you is that if it is a buffer, the color should stay the same when you add a strong acid or a strong base. So it's easiest to make an approximation and use this equation called the Henderson-Hasselbalch equation in order to determine what pH a buffer will have. So for example, your body wants to be buffered at a pH of about 7, wants to be neutral. So we'd need to have a buffering system that will give us that pH. So if we use acetic acid, we start out with the Ka expression, and we can solve for the H3O plus. So we haven't done anything here except just look at our expression for the equilibrium of a weak acid. And then we can take that equation from the bottom where we've rearranged it to solve for the hydronium ion concentration, and we can take the negative log of each side. So if we do that, they're still equal, and the left-hand side becomes pH, and the right-hand side becomes pKa, because the negative log of the Ka is the pKa, and then it'd be subtract off the log of the acid over the base. But when you take a log, if you want to take 1 over what's in your log, you just change the sign out front. So negative log of acid over base is the same as plus log of base over acid, just makes it easier to look at. So this equation is called the Henderson-Hasselbalch equation because it allows you to take some acid with a Ka and determine, if you make the ratio of the base to the acid a certain quantity, what pH you'll get. And so you can tweak that ratio in order to get the pH for your buffer that's ideal for whatever system you're making it for. Okay, well, we'll work problems with this in class. So the next application is something called a titration. So you've looked at titrations in Chem 107. And now we're going to think a little bit more about some of the things you can learn from a titration, not just the equivalence point, but you can also learn, in this case, with acids and bases, you can learn their Kas and Kbs. So a titration is a procedure for determining the concentration of a solution by allowing a carefully measured volume to react with a solution of another substance, the standard solution whose concentration is known. So you have learned about this in 107. Hopefully it isn't too distant. The equivalence point is the point at which stoichiometrically equivalent quantities, in this case, we're talking about acids and bases, have been mixed together. I'm thinking right now, it's a couple weeks before the class when I'm doing these. I haven't talked to Annalise, Dr. GB, about what labs you're doing, but I would assume you're going to do a weak acid titration. So this is showing you that you can find the equivalence point because the pH will change a lot at the equivalence point. And we'll also find that if you go halfway to the equivalence point, you can find the pKa. So when you're doing a pH titration curve, you're going to be using a pH meter rather than an indicator, and you're going to be adding your solution, whatever, if it's a strong acid or a strong base, from the burette and monitoring the pH. So then you'd be graphing pH versus the volume of whatever it is. So in this case, it looks like you're titrating, yeah, because the pH is 7, a strong acid with a strong base. And this is how I knew that the pH would be 7. So let's go through. So the reaction for a strong acid and a strong base really is, if you have a strong acid in water, you have hydronium ion concentration equal to that strong acid's original concentration. Same thing with the strong base. If you put strong base like sodium hydroxide into water, you'll have a concentration of hydroxide that would be equal to the base you started with. And the reaction pretty much goes to completion. This is the reverse of the dissociation of water. So if the reverse reaction has a K of 10 to the minus 14, this reaction has a K of 10 to the 14 because it would be 1 over that. So 10 to the 14 is pretty much everything went to product. So it's about 100% reaction. So before we add any sodium hydroxide, we have 0.1 molar HCl. And so the pH is going to start out at 0.1 because the strong acids H3O plus concentration, is going to start out at 1 because the concentration of hydronium is 0.1. The negative log of 0.1 is 1. So the pH starts at 1. And then we get to the point where we've added, let's see. Yeah, so when we're before the equivalence point, we have more acid than base. And so what they're saying with the arrow is that when you're before that point at which the pH changes rapidly, you're at the point where you have more HCl, therefore hydronium ion concentration than sodium hydroxide added. When you reach the equivalent point, they've been added in equal quantities. And so I just want to make sure. They're not really showing you how we calculate these. So in class, we'll also do a problem from each type of titration, but we'll just have to look at essentially when we're before the equivalence point, how much excess HCl do we have because we haven't added enough OH minus. And then at the equivalence point, we have equal quantities, so it's all reacted to make water basically. And then past the equivalence point, now we just have to figure out how much excess OH minus we have. So it's going to be acidic before the equivalence point, and then it'll have a sharp rise and it will become basic after the equivalence point. And this is going through and giving you the numbers, but it's not showing you the calculation, but we will do these calculations so you'd find where these points come from. The other kind of weak acid, or the other kind of titration that's important is weak acid with a strong base. And this one is one where you can figure out the Ka for the acid. So it gives you more information than just the equivalence point. So if we have acetic acid and we react it with sodium hydroxide, so sodium hydroxide's in the burette, we have some acetic acid in our flask. Before the equivalence point, we have not reacted away all of our acid. At the equivalence point, we've added equal quantities. And then past the equivalence point, the pH is just going to be dependent on the excess OH minus that didn't have any acetic acid to react with. These are just showing you some of the curves and their different shapes based on their Ka. So if it's a fairly strong weak acid, like Ka 10 to the minus 2, you're going to have a bigger change in pH as you go through the equivalence point, where if it's a fairly weak acid with a Ka of 10 to the minus 10, the red line, it's not going to be very pronounced at all. This one we're not going to do. So this we will take a lot of time in class to work through and actually calculate these points. This one we're going to skip because it's almost the same as the weak acid strong base, and we just probably don't need to do it all. And we won't do one for polyprotic acid. So for polyprotic, it probably would make sense to you that you're going to have two equivalence points. The first point would be when you've reacted away all the first proton, and in this case it's diprotic, so then you'd also have another one when you've reacted away all the second proton. But doing this titration would tell you two things. It would give you the Ka1 and Ka2, and it would also tell you that both protons are acidic because you have two equivalence points. And that is all we're going to do as together as a class. The rest of the chapter, these are going to be topics for your projects that you're going to present: solubility equilibrium, complex formation equilibrium, quantitative analysis based on these equilibrium, things like how does pH impact solubility. These are all super important, and you'll find lots of applications, I think, within areas that you're interested in. So for example, the pH changes the solubility of lead compounds. And so when you look at the Flint, Michigan water crisis, it really was a result of changing the water source, which changed the pH of the water. And with a different pH, more lead was soluble that had been coating the inside of the water pipes. So the rest of the chapter, we're not going to go through together and you're not going to be tested on, but you're going to use examples from things you're interested in to help your classmates learn about these other applications of equilibrium. Yeah. Okay, so we are done with that chapter.